When you're looking to solve logarithmic equations, sometimes it can be pretty simple. Sometimes it can be a little bit more advanced. Well, in this video, I have compiled my best examples of me solving logarithmic equations step by step. We work with the most basic examples and then go ahead and advance to more difficult problems that you would expect to see on a test or a quiz, or that maybe you are struggling with. They're all compiled inside of this video, and I hope you enjoy. So what I'd like you guys to remember is there's a couple properties that we're going to be using for this, and basically what we'll need to do is we need to get rid of this logarithm. So what we can do is use the property that e to the ln of x is just equal to x. So what I can do is kind of raise these both with the base e. Now, by using the one-to-one property, not one-to-one property, but using this property, I now have x minus 3 is equal e squared, add 3, and I have x equals e squared plus 3. And then the problem says to approximate to 3 decimal places, correct? So I'll take my calculator and I'll just do e raised to the second power, and then plus 3, and I get 10.389. And there you go. When looking at this problem, again, ladies and gentlemen, I'm giving you another equation, right? Another equation for you guys to go and work on. So we can't solve it right now by using our properties of equality with exponents, right? But what can I do? What have I learned to do with a logarithmic equation? I can always transfer it to exponential. So to rewrite an exponential, since we've done so much practice with this, it's 3 raised to the 5th power equals 4x minus 17. So now, how do I solve this, though? How can I rewrite 3 to the 5th power, or 4x minus 7 to the base 3? No, that's not going to work, right? But can I evaluate 3 to the 5th power? Yeah. So somebody has a calculator for me? You're the man. 3,000 what? Equals 4x minus 17. Now can I solve a problem like this? You bet you can, Yesenia. Well, that's good to know while I'm teaching what you're supposed to be learning. Good. I'm happy to learn that. So we have 300 and 100 and, let's see, 42. So as I'm working my brain on mathematics. And then x equals, Austin? And there you go. So now the next one, Jamie, and this one gets a lot of students because we're dealing with a lot of decimals, which I'm going to need to tell you guys, make sure you plan ahead, as I mentioned with calculators, so you can prepare for it. In this example, again, we need to undo multiplying by 16, so I'm going to divide by 16. So I have ln of x equals 30 divided by 16. And that equals 1.875. I will recommend, guys, at any time, always when you're using a calculator, try to use the whole decimal. Do not round until the very, very end. Because if you round initially, for instance, if you just say, oh, well, that's 1.9, your answer is going to be off. All right? So make sure you always use the complete decimal form from your calculator. Then, to solve this, I need to put this in exponential. So I would take, remember, this is base e, right? We don't write it there, but when we're knocking the natural logarithm, we know it's there. So therefore, I have e raised to the 1.875, and that equals x equals 6.52. And again, we're using our calculator. We are rounding, so it's going to be an approximate value. All right, natural logarithm equation with the square root. Perfect. Now, there's a couple ways we can go through about this. We automatically know that we have a logarithm naturally exposed here. So therefore, I could just go ahead and rewrite this in exponential form. So it'd be e to the 5th equals the square root of x minus 8. Then to solve for my x, to undo my operations, I need to undo the square root. So I'd square both sides. So now I have e to the 10th equals x minus 8, and then I can simply just, I don't know where at 10 comes from, and then just add 8 to both sides. So therefore, x equals e to the 10th plus 8. So therefore, I need to calculate that. So I'll do e raised to the 10th power plus 8. And therefore, that answer is going to be x equals 22,034.47. Now, another way you could also do this is you could also bring that, you could also use your properties of exponent or of logarithms of x minus 8 equals 5. You could rewrite that as ln of x minus 8 to the 1/2 power. Then you can bring that in the front, so it'd be 1/2 equals 1/2 times the ln of x minus 8 equals 5. Multiply by 2. So then you'd have ln of x minus 8 equals 10. And then, again, by converting this now to exponential form, you'd have e to the 10th equals x minus 8, which is the exact same thing we had over here. So that's a way of using your properties of logarithms. Or if you just prefer using your inverse operations, that would work as well. So now that Sam's awake, good weekend. We can go ahead and take a look at this. And we need to look at what properties we're going to want to use. Okay, James?
Yes, sir.
All right. So first of all, before I can even do any kind of properties, we always want to get rid of kind of what we say, like all this extra stuff that's going on. I'm multiplying my function by 6. I can get rid of that, right? Before I start getting into logarithms, I know I can get rid of that. So I'm going to divide by 6 on both sides. And I know that's going to give us something nasty, 11 divided by 6. It's not rational, but, or, you know, it's not going to be an integer, but that's okay. Log base 3 of 0.5. 11 over 6. Yes?
Couldn't you have taken the 6 and made an exponent?
You could have made it a 6 as an exponent as well, yes. Our problem is, though, that's not really going to, well, it's nothing wrong, but what's going to help us is that's as an exponent, right? Exponents mean, if that's an exponent, then you're going to have to take the 6th root of something to get rid of an exponent, right? So you always, it's probably helpful to understand that rule to always want to keep your exponents in front. But yes, you could have rewritten as the 6th power, but then you need to remember, Audrey, that if you have it written as a 6th power, you have to take the 6th root to get rid of it eventually. So helpful, try to always write them, keep them like this, because I'm sure you'd probably rather deal with dividing and multiplying than dealing with roots. But you would get the same answer if you worked it out that way. All right, so now I have this equation, right? So now what we need to do is figure out, well, what property of logarithms can I use now to solve for this? And we're going to use a couple of properties. You guys remember this property. Log base a of a equals x, right? The same thing is true. There's a very similar property that says a raised to log of a of x equals x. So when I said that you guys need to know your properties like inside and out, I wasn't joking, all right? You guys have to know these properties. They're very, very simplistic, but if you guys can just have these properties memorized, it's going to make your life doing this test, yeah, very, very easy, okay? Please, guys, go back and study these properties so you understand. You guys should know, oh, I'm sorry, that's raised to the x power. You remember that log, whenever you're taking the base of a, of evaluating a raised to the x power, that equals x, because a raised to a raised to what power gives you a? That's 1. So you just cancel out, you're left with x. Here, it's the exact same thing. Whenever you have a number and you're raising it to a logarithm of the base of what that base is for your exponent, it's going to equal x. Then the next two properties we've talked about is, I go over this example all the time. So you guys should know that you have log of x equals log of y, then x equals y, right? That's the one-to-one property. The same thing is true with this. If I say, if I was to work this backwards and I said x is equal to 10, then you could also say 2 raised to the x equals 2 raised to the 10, right? You could take you could make whatever base you want to. As long as, if you say x equal to 10, you could make them as exponents. It doesn't matter as long as your bases are the same. Does that kind of make sense? Right? Just like I could say, you know, x plus 10, or I'm sorry, x is equal to 10. You could also say x minus 1 is equal to 10 minus 1. As long as you do it to both sides, that's okay. So what I'm looking at here is I have a logarithm. I need to get rid of this logarithm. There's two ways I can get rid of the logarithm. One, I could transfer it to exponential form. This is logarithmic form. I could transfer it to exponential form. That is one way. The other way you could do it is you could also say, well, what happens if I raised both of these to from the third power, or from the base of 3? So I log base 3 of 0.05. Why do I keep writing that like that? 0.5x. Thank you for adding that. And the reason why I'd want to raise both of these as exponents with the base 3 is because now, using my rule of law properties of logarithms, I know this is now just going to equal, that's just going to cancel out the 1, so I'm left with 0.5x equals 3 to 11 over 6. Did everybody see the jump I made?
No.
Yes, Mom.
Wouldn't you get that same result from just changing it to exponential form?
I know, that's what I did.
Yep. And there's absolutely nothing wrong with that. I'm going to show that next, too. It's just a different way. I'm just showing this elongated way, too. Because it is helpful, though, to understand that you guys can raise it to the same power to get rid of that logarithm. Because whenever you guys are getting rid of the logarithm, you have to understand there's a couple ways. And sometimes transferring it to exponential form might not be always the simplest way to see it. And then from here, I just divide by 0.5. So therefore, x equals 3 to 11 over 6 divided by 0.5.
It's not right though.
But they got 2.
It's 2. That's what I got too.
Yeah,
but they have a 2 in front of the 3.
But you get the
Okay,
same
hold
answer.
on. We'll just go ahead and look at the answer, okay? I'll just go through it and I'll look at the answer. The other way, like I said, that we can go back through and look through by changing it to exponential form, what Vaughn was saying is you could also just say, remember guys, what does the logarithm says? It says 3 raised to what number gives you 0.5 raised to x? So it'd be 3 raised to this. So you can easily just transfer it to exponential form, right? Just change, that's logarithmic form. This is exponential form. That's what we did in what, section 3.2? You guys need to know that over and over and over. Then you can just divide by 0.5. Okay, and that's the end.
Well, on this example, the main important thing, guys, we need to do is isolate. But just like if we're solving anything else, if we had 1/3 x plus 5 equals 7, and I said to solve, the first thing we always do is undo addition and subtraction first, then do undo multiplication and division. So the first thing you want to do is subtract 5 on both sides. Therefore, I have 1/3 log base 2 of x equals 2. Now, to undo multiplying by 1/3, I could divide by 1/3, or I could multiply by the reciprocal on both sides.
That's much easier.
So now I have the equation log base 2 of x equals 6. Now, to go ahead and rewrite this, to solve for this, I can rewrite this in exponential form, which would be x equals 2 raised to the 6. And 2 raised to the 6 is going to equal 64. So what this does involve is you guys using some thinking. And thinking about it, it's like, all right, well, Mr. McLogan didn't go over it, but he only went over 2 things. Either using the one-to-one property, or he went over converting it to exponential form. Now, if you guys look at this, I don't have more than one logarithm. I don't have a logarithm set equal to a logarithm. So I cannot use the one-to-one property. So what I want you to think of, well, if I can't use the one-to-one property, then let's look into using converting it to exponential. But I can't convert this to exponential form until it's written in logarithmic form. So the first thing I need to do, you guys can see, I can't write in logarithmic form until my logarithm is isolated. So the first thing I need to do is add a 10 to both sides. Then I have it in log base 3 of n plus 3 is equal to 0. Now I have it in logarithmic form. And what we practiced and what I showed in my notes is converting log form to exponential form, which would be 3 to the 0 equals n plus 3. Now, anything raised to the 0 power is 1.
1.
So therefore, I have 1 equals n plus 3. Subtract 3, subtract 3, negative 2 equals n. Go ahead, check my answer, and that works.
Oh, so what we have here is 3 times log base 5 of x squared plus 9 minus 6 equals 0. So what we want to do for this problem is we want to be able to see how can we isolate our logarithm so that we can then transfer it over to exponential form. Because we can't right now convert it over to exponential form to solve for our value of x until it's in our logarithmic form and it's isolated. So right now we notice there's a couple things. First of all, I have this 6 over here. Well, I can't convert this over to exponential form when I have an expression, with a term. So I'm going to want to get this 6. First thing we want to do is isolate it by providing the 6 over there. So now I have 3 log base 5 of x squared plus 9 equals a positive 6. Now the next thing I need to do is use the power rule of logarithms to rewrite the multiply by 3 as my exponent within my logarithm. So remember, the power rule of logarithm states if you have a number multiplied by your logarithm, you can rewrite that as an exponent inside your logarithm. So therefore, I can rewrite this as log base 5 of x squared plus 9 cubed equals 6. All right? Now, you can see that this is in logarithmic form, right? So now, to solve for this, I can now rewrite this in exponential form. So I can rewrite 5 to the 6th power equals x squared plus 9 cubed. All right, and that's so important because now I'm in a point where I can see how I can solve this. Now, usually when we had exponents and powers, we try to get them to the same base, right? Well, here I have a base of 5. Here I have a base of x squared plus 9. That's going to be a little difficult. However, just by using our solving, if I had x squared equals 4, to solve for that, you take the square root, both sides, right? If I have x cubed equals 8, you take the cube root. So here, I have x squared plus 9 cubed. Let's take the cube root of both sides. Now, the other thing to remember is the cube root of x is equal to x to the 1/3 power, right? So I'm just going to rewrite that as, x raised to the 1/3 power to help us out. So therefore, I have 5 to the 6th power times the 1/3 power. And the reason why I like to do that is because now I can apply the power of power rule of exponents. And remember, when you have an exponent raised to another exponent, you multiply them. So 6 times 1/3 is going to be 2, which is just going to leave me with 5 squared equals x squared plus 9. Well, therefore, let's continue this work over here. So now I have 25 equals x squared plus 9. So now I'll subtract the 9. And therefore, I get 16 equals
Miss Mills,
x
please call the
squared.
main office. Paulette Mills,
Now,
please
to
call
finish
the
this
main
up,
office.
I'll take the square root of both sides, and I get x equals plus or minus 4. So there you go, ladies and gentlemen. That is how you solve a logarithm, by isolating it, using the power rule of logarithms, and then solving. Thanks. So the main important thing that I want to look at, Tim, if you remember this, 2 to the 4th equals 2 to the x plus 1. What was when we had this equality, what did we know that we could do? When we say 2 to the 4th power equals 2 to the x plus 1. OK, let me help you out. What does x have to equal in this equation?
4.
Has to equal 4, right? If it's 2 raised to this power 4, then the x has to be raised to the 4th power, right? And then if I just say, I don't know, let's just add 1 there. Well, you know the answer is 5, right? Or actually, sorry, the answer would be 3. But what you can do for this is actually eliminate now our bases. So then we're just left with 4 equals x plus 1. Then you can solve for x. Does that make sense? So whenever that was part of, Chris, when we had those other equations, it was important not just to convert it to exponential to logarithmic, but to be able to apply this property that when we have the same base, or we at least got to make sure we can raise them so they have the same base, then we know the exponents are equal to each other, or the powers are going to be equal to each other. Now, what we talked about when we had logarithms was that logarithm converted to exponential, right? Now, this might be one you probably wouldn't want to convert to exponential. If you convert this to exponential, you're going to have 2 raised to the log base 2 of 2x plus 8 equals 4x minus 6. That kind of looks like a pretty crazy problem to go and try to do, right? And then you somehow have to raise 4x minus 6 to the 2 power, but still, you still have a logarithm that we're not really helping ourselves out with. So we're going to have to be able to see if there's another law of equality that we can use. And let me just kind of go through this. We know that log base 5 of 25 is a billion variantos. Do you know what this answer is? Let's see what the logarithm again says. Log base 5 of 25 says 5 raised to what power equals 25? 2, right? So this answer is 2. Yes? Yeah. OK. So what if I said log base 5 of 25 equals log base 5 of x? What does x have to equal, though? 25, though, right? You know that 5 is going to, if this is equal to this, you know that 5 has to equal 25. So does it really matter if we have this log base 5 here? No. You can just say 25 is equal to x. Notice how that's very similar to our equality, exponential equality form, right? The law of equality for exponents. As long as the base of the logarithms are the same, and you have one logarithm equal to another logarithm, we're not concerned about the logs. So therefore, what you guys notice for this, are we concerned then what log base 2 is? No, we just know to solve for x, we know that these have to equal each other. So what I'm going to do is forget about log base 2. They're not going to help me figure out x. So now I can just say 4x minus 6 equals 2x plus 8. Now I have two x's, but the thing is those x's are linear, right? So all I need to do, I can combine them on the same side. So what I'll do, Cody, is I'll subtract the 2x on both sides. I get 2x minus 6 equals 8. Now I isolate the variable by adding 6 to both sides. So I get 2x equals 14. Divide by 2, x equals 7. And there you go. OK? That's it. So it's just like our equality property of exponents. If you have logs that are equal to each other, you can cancel them out. So what we're going to want to do for this one is I have log base 13 of x squared minus 4 equals log base 13 of 3x. So ladies and gentlemen, remember when we take off our hats that we can apply the property of equality with logarithms. And the property of equality of logarithms says as long as we have a log to the same base, then Isabellina, we can evaluate, as long as we have to the same base and they're isolated, we can now undo them because they're not going to affect our problem. If we know that we're evaluating logarithms to the same base, what we're evaluating them for has to be equal. So therefore, we're not really concerned about log base 13. We just know that x squared minus 4 now has to equal 3x. Now the issue we have here is now we have a quadratic term. So we have to solve this. So solving quadratics, we need to make sure we set equal to 0. So therefore, I have x squared minus 3x minus 4 equals 0. All right. OK? Just rewriting it, right? Watch. 5 minus 4, is that the same thing as, here, negative 5 minus 4, is that the same thing as negative 4 minus 5? It's the same thing. So you're just rewriting it. OK? Good point. So if you just square, let's say you, so square root the x, right, from here?
Yeah.
Oh, but yeah,
You have to make sure you square root the 4, and then you're crazy. And then plus, you don't have, then your answer has an x in it.
Yeah,
Well, you can't solve an answer when you have an x in it. When
side.
your property, which is called the square root property, that would work if it just looked like this. Then you just add the 4, and then you can take the square root. That only works when there's a squared term, but it's only one of them. Now that we have two, we have a squared term and a linear term, we have to either complete the square, factor, or quadratic formula. So let's start off by factoring. What two numbers multiply to give you negative 7, add to give you negative 3? We can factor this to x minus 4 times x plus 1 equals 0. And the reason why we like using factoring is because now I can apply the zero product property, which states x minus 4 has to equal 0 and x plus 1 has to equal 0. So therefore, x equals 4 and x equals negative 1. OK? Questions? Anything else? Isabelina Barrientos? All right. The next example. This one gets a lot of students, rightfully so. It is a quadratic. Oh, basically, first of all, it looks very confusing from the start. So the first thing we want to do is notice that, hey, it's a logarithm equal to another log. So cancel them out. V squared plus 35 equals negative 12v minus 1. And please, ladies and gentlemen, as you leave my classroom and go to other math classes, please remember when you're solving quadratics, you cannot solve this when you have a quadratic with more than one variable. One's quadratic and one's linear. You cannot solve it using like the square root method or using inverse operations. You have to use factoring. So therefore, we have to get everything to the same side. So I'm going to add a 12v. Well, 12v is not like terms with v squared or 35. So it's v squared, and then I'll add 1 as well. So it's v squared plus 12v plus 36 equals 0. I added the 1 to both sides. So I could add the 1 to 36, as you guys can see. That's how that worked. So now, so what I did was I added 12v to get rid of the 12v here, and I added that on both sides, and I added 1 on both sides. So now there's nothing left over here, right, except for 0. And I added everything over here. Now, why would I want to do that? Because remember, quadratics, the first thing we learned in solving quadratics, you had to set them equal to 0. Then, once you set them equal to 0, what two numbers multiply to give you 36 and then add to give you 12? 6 and 6. So v plus 6 squared equals 0. So v equals negative 6. OK? And then as you guys plug that in, you guys see that that works. So therefore, that is your answer.
When taking a look at this problem, Kristen, what we're going to want to do is, ladies and gentlemen, remember what we were talking about. Let's go back, I think, Sadiq, my favorite example, which I've probably outdone. 2 to the x equals 2 to the third power. If I say 2 to the x is equal to 2 to the third power, we know that x now has to equal 3, right? Because the base doesn't really matter. If you raise 2 to a power that you don't know, and that's equal to 2 to a power of 3, you know that the powers have to be the same, right? Okay, now, is exponents related to logarithms in any shape or form? Yeah, remember when we did, so if I say log base 2 of x equals log base 2 of 3, the exact same thing is going to occur. Because remember when we changed from logarithmic to exponential form, Juliana? When we changed from logarithmic to exponential form, remember the base was always the same, right? You guys remember that? The base remains the same when you transfer from logarithmic to exponential, or from exponential to logarithmic. The base is always the same. So in this problem, I know these are different how I wrote them, but all I want you guys to understand is if I have the log base 2 of x equals log base 2 of 3, the base and the logarithm aren't going to matter. We know whatever we're evaluating them for have to equal one another. So in this case, since I have log base 4 equals log base 4, I now know that x squared minus 4 has to equal negative x plus 2. So now it comes to an algebra problem where I have to solve this. So we notice it's a quadratic with the x squared. So now I have to set it equal to 0 and see which ways I can factor it. So by factoring equal to 0, what I'm going to do is I'm just going to add and subtract an x and a 2 on both sides. So therefore I get x squared plus x minus 6 equals 0. Now there's a couple ways we learned how to solve a quadratic. We could factor, complete the square, quadratic formula. We could graph it and find the intercepts. All right. So for this one, I always like to go and see, though, can I factor this, right? And you guys can remember the old one, negative 6 and 1. What two numbers multiplied to give you negative 6? I had to give you 1. Very good. So x plus 3 times x minus 2 equals 0. And the reason why we like to factor it is because now once it's factored, now I can apply the zero product property, which states x plus 3 equals 0, or x minus 2 equals 0. So therefore, our solutions is x equals -3 and x equals dos. Cool? Cool. Right now I have log base 4 of x minus log base x minus 1 equals 1/2. Whenever you have multiple logarithms, go back looking to your properties logarithms to try to condense this down to one logarithm. Ladies and gentlemen, when we had an equation and it looked like this, 3x plus 4 plus x equals 5. And I said to solve this, we know we have two x's. We need to solve for an x, right? So what did we do with the x's? We combined them, right? Because you can't solve when you have two different x's, right? Unless you're going to be doing some factoring technique when it's like x squared or x to a higher power. So we can't solve this unless we combine these. Well, the exact same thing, when you guys have multiple logarithms, you're not going to just be able to isolate and solve for a logarithm. You have to condense them down to one single logarithm. So we notice that our properties of rules state that when we have the difference of two logarithms, we can rewrite that, as long as they have the same base, as the quotient. All right. Now, I can rewrite this into exponential form, which would be 4 to the 1/2 power equals x over x minus 1. All right. Or I could use my one-to-one properties and raise each power, raise each to as an exponent with the base 4. So now, ladies and gentlemen, when we take a look at this, well, 4 to the 1/2 power is equal to the square root of 4. So therefore, this answer is 2 equals x over x minus 1. So now, to solve for this, we need to get x minus 1 off the bottom. Sam, do you have this written down?
Oh, I get it.
OK. So now, Adara, we have this. You can simplify this now to get your x to the same side. And therefore, x equals 2. OK, what I like to do is show you guys how to solve a logarithmic equation that looks something like this. So, man. We got a lot of issues with this one. And the first thing I want you to try to think of, remember when you're solving for equations and you had x plus x like equaled, I don't know, 8. Well, you can't, remember our whole goal of solving equations is to get to x equals, right? So you couldn't do anything unless you combined your x's. Then you could divide by 2 and you got x equals 4. Well, logarithms is the same thing. We can't use any of our log property or anything special unless we only have one logarithm, right? Or if our equation's in logarithmic form. So what I'm going to do is I'm going to have to combine these. Now, combining variables had its own rule. If you have an x plus an x, it's 2x. However, combining logarithms have its own rules as well, and that's the properties of logs. And what it states is, if I have a logarithm subtracting another logarithm and they have the same base, I can combine them by division. Now, remember, this 2 I can rewrite as an exponent. So I'm going to do that first. I'm going to write log base 2 of x squared minus log base 2 of x plus 3 equals 2. All right, that's another properties of logs that you can take your multiplier and put it back as a function. So now I'll rewrite this as log base 2 of x squared. I'm sorry, let's change this around a little bit. As x squared all over x plus 3. So now I'm taking the function of both of these combined divided equals 2. All right, now we need to remember a couple rules. First rule is an inverse property. And what the inverse property states is, remember what a logarithm means, guys? if I say logarithm of 3 to 9, that means 3 raised to what number gives you 9? And we know the answer is 2. So if I say log of 3 raised to the third power, 3 raised to what number gives you 3? Well, the answer is 1. So if I said log base 3 of 3 is equal to x, that answer is going to equal x. Well, why does it equal x? Well, remember, I can take that number, I can take my exponent and put it in front as I showed you here. So I could really rewrite this as x log base 3 of 3 equals, well, log base 3 of 3 is 1. 1 times x is 1. I'm sorry, x. Okay? So this works the exact same way. So that way, hopefully, it's easy to understand. It works the same way if I was going to say 3 raised to the log base 3 of x. Okay? So you could say this is going to still cancel out to equal x. These two cancel out just like they cancel out there. Okay? So what I want to do is I need to get rid of this logarithm. Now, there's a couple ways you could do this. You could just rewrite it in logarithmic form, in exponential form, which 2 raised to the second power equals x squared divided by x plus 3. Or what we could do is we could also exponentiate each side to the base 2. Therefore, those two would cancel out, and I'd be left with x squared over x plus 3 equals 2 squared. Now, if that just really confused you, just think of this way. Just put it into exponential form. 2 raised to the second power equals this. Okay, it's the same thing. 2 squared, I'm going to rewrite as 4 because I'm kind of running out of space. So now what we have, that's a horrible 2. So now what we have is we have an x squared divided by x plus 3 equals 4. Well, I need to remember we got to get rid of this x, right? And one thing I noticed is since I have an x squared, I'm going to have to do some kind of factoring, square rooting, completing the square, or quadratic formula. I'm going to have something's going to be going on like that. And since I see this other x, I'm pretty sure it's going to be a factoring or a quadratic formula problem. So, or completing the square. So what I need to do to get this off, I need to multiply by x plus 3 on both sides. Therefore, those will cancel out, and I'm left with x squared equals 4 times x. Let's write that a little bit better. 4 times x, as I do distributive property, plus 12. Then, let's get them all to the same side by subtract. So x squared, let me show you. So now, let me explain why I'm having this. So I have x squared equals 4x plus a 12. Remember, when solving for x, you always want to get your x's all the way to the same side, right? Now, when you have a quadratic, or anytime you have your x's raised to a different power, we want to see if we can set them as into linear factors. Because what I can do is I can use the zero product property rule, which states that any two numbers multiply to give you 0, one of those numbers has to be 0. So we can use that to find out factors. So what I'm going to do is I'm going to subtract a 4x onto both sides. Then I'm going to subtract a 12 onto both sides. So therefore I'm left with x squared minus 4x minus 12 equals 0. And then I say, can I factor this any further? And you say, yes. The two factors for this would be x minus 6. So the two numbers that multiply to give you negative 12, but add to give you a negative 4. So x minus 6 and x plus 2 equals 0. So since these two numbers, or these two factors, multiply to give me 0, I can set them both equal to 0. And say that x is equal to 6, or x is equal to, x is equal to 6, or x is equal to a negative 2. Now those are my two possible solutions. But what I'm going to do is I'm going to plug them back into my logarithm and see if they both work. So I plug 6. So if I take log base of 6, that's going to work. However, if I take log base of 6 plus 3, that's going to give me 9. That one does not work. Then I go ahead and take a look at this problem, and I say x equals a negative 2. Well, if I plug in x equals negative 2 in for there, and for this function, I can't evaluate x equals a negative 2. So therefore, that one is not going to work, because you can't take the logarithm of a negative number. Okay? So therefore, that will not work. But if I put a negative 2 for there, it would work. But anyways, that is an extraneous solution. Does not work. So x equals 6 is your only solution. Okay, what I'd like to do is show you how to solve this logarithm. So first of all, to solve this logarithm, what we need to look at is I need to see, all right, how can I, first of all, condense this down, right? Because what you notice right here is I have 3 logarithms. So that's way too many things to be dealing with. So what I want to do is I want to use my properties of logarithms, condensing it to get this down to at least 2 logarithms. I can condense these. Remember, whenever you have a log subtracting another log, you can condense them by division and using 1 log. So I'll have this can be reduced down to log of x plus 8 divided by x equals, and this could be 2 log of 9, but also remember, whenever you have a number in front, all right, you can rewrite that as your exponent. So I have log of 9 squared. So now what happens is we can use our one-to-one property. Whenever you have a log equal to a log, and that's one thing you always want to look at when you're solving logarithms, always look for, see if you can get it a log equal a log or a power equal to a power. Because then you can use your one-to-one property to cancel them out. So now I have x plus 8 over x equals 9 squared, which is 81. Well, from here, I have an x on the top and an x on the bottom. So to get rid of my x on the bottom, I'll multiply by x on both sides. Therefore, I have x plus 8 equals 81x. All right, I will subtract now an x, and I'll get 8 equals 80x. Then what I'll do is divide by 80. Okay, and then you can see you can divide the top and the bottom. So therefore, I have x equals 1/10. And that's how you solve a logarithm.
So on this one, I have log base 10 of x plus 4 minus log base 10 of x equals log base 10 of x plus 2. So to do a problem like this, ladies and gentlemen, again, we can only solve when we have our single logarithm. So let's go ahead and convert this to log base 10 of x plus 4 over x equals log base 10 of x plus 2. Now we can apply our one-to-one property. We have a logarithm equal to another logarithm. So therefore, we know that what we're evaluating each logarithm for, since the bases are the same, are going to be equal. Now, again, to solve for this, we need to multiply by x on both sides. So therefore, I have, that goes to 1. So I have x plus 4 equals x squared plus 2x. Now, since I have a quadratic on my right-hand side, are you writing? Did you already do this one? Huh? Yeah. All right, well, let's take it out so you can check it. Then I subtract the x and subtract the 4. So I have 0 equals x squared minus or plus x minus 4. So we look at this and we say, all right, is it factorable? No. So how else can we solve something when it's not factorable? We can always go back to quadratic formula. Remember quadratic formula, when you have something in the form of y equals ax squared plus bx plus c. Therefore, it's x. The zeros are going to be x equals opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2a. So in this case, you can say a equals 1, b equals 1, and c equals negative 4. So now we plug them in. So I'm going to have negative 1 plus or minus the square root of 1 squared minus 4 times a times c divided by 2 times 1. So it's negative 1 plus or minus 1 squared is 1. That's going to be plus 16. So it's going to be the square root of 17 divided by 2. So you have negative 1 plus or minus the square root of 17 divided by 2. Now, you're going to have a positive and a negative answer. Now, I know their answers are going to be irrational. But remember, when we're checking for extraneous solutions, Gabby, do you have this one written down? Yeah. OK. So when you're checking for extraneous solutions, remember, we're going to take whatever these answers are, and we're going to plug them into this equation. Now, I'm plugging in log base 10 of x. So if I plug in a negative number, it's going to create an extraneous solution. Yes? Extraneous means it's not a part of the domain. All right? And if you remember when we graphed the logarithmic function, it looked like this, right? And what I meant is those x values, the domain was only restricted to positive numbers, right? So what that meant is when we're talking about a logarithm, we can only plug in positive numbers. Does that make sense? Now, it doesn't mean if you have a negative number, it's automatically extraneous. Because what if my logarithmic equation was log of x plus 10? Right? Well, that means if I put in a negative 2, is my answer still positive inside the parentheses? Yeah. So it doesn't mean just because you have all negative, just because you have a negative number, it's extraneous. Because your equation could be shifted to the left. However, what I want you guys to understand is here, there's no transformations. This is log base 10 of x. The domain of that is from 0 to infinity. So if I have a negative answer out of here, which I am going to, that answer is going to be extraneous, meaning it's not going to be a part of my domain. So to figure that out, I take the square root of 17, and I do -1 minus that answer, and then divide it by 2. And what I have is x is approximately -2.56. Well, that answer, ladies and gentlemen, is extraneous. Because if I put that answer in for that, and I try to evaluate what is the log base 10 of -2.56, that's not going to work. It's going to be extraneous. However, if I do -1 plus the square root of 17, and I divide that by 2, I'm going to have an answer of x is approximately 1.23. And I notice if I put in 1.23 into each one of these, I'm always going to have a positive value. Therefore, that is going to be my only solution. OK?
Wait, because that one's not extraneous?
That one's not extraneous. Because you can plug that in into each one of these logarithms, and you'll get an answer.
What makes -2.56 not extraneous?
Take your calculator. Take log of -2.56. And tell me what the answer is. Right. You can't take the logarithm of a negative value. So if you plug in a number and it gives you a negative a logarithm of a negative number, that solution is extraneous. 1.2, I took -1. I added it to the square root of 17. And then I divided that by 2, which was 1.56. Is that what you got? Yeah. I just probably. Sorry. It's 1.56. So if we have more than one logarithm separated by addition, this whole expression is A. This whole expression is B. OK, so I know it kind of gets a little bit confusing because technically when we did this, we just had numbers there, right? It was like log of 8 plus log of x. And you're like, OK, that's log of 8 times x. Well, now the values are actually expressions separated by addition and subtraction. But that doesn't change what the rules of logarithms tell us to do. And then here, I can use the power rule. I can put that up top. OK? Does everybody understand what I did? Everybody OK with that? All right. So now, the next thing is, hopefully you guys see that now I have a logarithm equal to another logarithm. Since they're both ln, we know that the base is going to be e. So now I can just set this left side equal to the right side. And then obviously, I can go ahead and do my math here. When using FOIL, I get 3x squared. That's going to be minus 3x, so minus 5x plus 2 equals x squared. Now, obviously, I will need to solve for x. I notice that this is a quadratic. I remember from Algebra 2, when I want to solve for quadratics, I want to set it equal to 0 and solve it. So a lot of you guys did a very good job. You tried to see if it was factorable when you had the wrong equation. And once you knew that it was not factorable, you immediately went to the quadratic formula, which is exactly the process I would ask you to follow, because not every quadratic is going to be factorable, right? That's why we have the quadratic formula to help us out. However, how the actual real equation is presented actually is factorable. We could have this as 2x minus 2, or no, minus 1, and 2x minus 2 equals 0. I think that worked. No, there's something wrong. What did I factor this wrong? It's x minus 2, that's right. Yes, there we go. Yep. OK, now the reason why we like factoring is because now we can apply the zero product property. So I can say 2x minus 1 equals 0, and x minus 2 equals 0. Therefore, x equals 1/2, and x equals positive 2. Now, here's one thing I didn't talk about in the last problem, because a lot of times this doesn't really come up, but it is very important for us to take a look at the solutions that we have for a logarithm. Ladies and gentlemen, when we talked about an exponential graph, it looks something like this. Was there ever any restrictions on our domain? Domain's all real numbers, right? All real numbers. Don't even have to worry about it. However, when we look at a logarithm, we have restrictions on our domain, right? The domain is nothing to the left of that asymptote, right? There's no negative numbers in our domain, correct? Now, you might think about this and say, oh, well, we're good, right? We have 2 positive numbers, so we're good. But you don't know what transformations actually occur in this graph at all. So what we need to do is to make sure our answers fit the domain. For instance, if you guys remember this, what did we do here? You know, x plus 3, 2x. If I said here's an equation, right? We know what answers are not a part of the domain, right? The answer that makes the denominator 0 is not a part of our domain, correct? Well, the same thing goes for a logarithm. We have restrictions on our domain. Based on the graph, we know that negative numbers are not a part of our domain. So what I want you guys to do is take your solutions and plug them back into x and for your logarithms. If you have to take the log of a negative number, you know that is not a solution. So if I plug in 2, 3 times 2 is 6. 6 minus 2 is 4. So that's fine. 2 minus 1 is 2. And then this would be 2. So are these, I'm taking my solution and plugging them in for x. Do you guys see, Megan, when I do that, I can evaluate for each logarithm. Now watch. When I do 1/2, even though 1/2 is positive, when I do 1/2, 3 times 1/2 is 3/2, which is 1.5. 1.5 minus 2 is negative 1/2, or negative 0.5. Can you take the logarithm of a negative number? No. So guess what? This is not a solution. So even though algebraically we found it to be a solution, that is our only solution of this equation. OK? So make sure you guys don't find fault and just say, oh, I got my solutions, and then just be good with it. Make sure you have to go back and check your solutions to make sure they're not going to be extraneous.
OK, for this problem, what I want to do is show you how to solve log of x, log base x, of 32 equals 5/2. So to do this, again, what we're going to want to do is transfer this to exponential form. So remember, what I always like to remember is log base 3 of 9 equals 2. That just reminds me 3 raised to the 2nd power equals 9. So I always write this as 3 squared equals 9. It just always reminds me of this. So when looking into this problem, we're going to do the same thing. X equals 5/2 equals 32. Now I've come up to a little problem here, right? Because how am I going to get rid of 5/2? Well, if I had x squared equals 16, to get rid of the square root, you would square both sides, right? So that would just be left with the square root of 16. Well, so x would equal the square root of 16, as these would cancel out. Well, what exactly is the square root? The square root of x is the same thing as x to the 1/2 power. So what I'm going to do is, and what I'm trying to say is, if I had x squared, and what I did was I raised that to the 1/2 power, that would still just leave me x. So that's something I can do here. What I'm going to want to do is, rather than, rooting it and squared, I can just write this as x to the 5/2. And what I'm going to do is I'm going to raise both sides to the 2/5. Well, what will happen here is I'm going to get x equals 5 equals 10 over 10, so it would be x to the first power, as those are going to cancel out, equals 32 to the 2/5. Now you might say, all right, well, you didn't really improve too much because now I still have 32 raised to the 2 over 5. So what am I going to do now with this? Well, you could just use your calculator and, say the 5th root of 32 squared. That's perfectly fine. We could just write it like this. 32 equals the 5th root of 32 squared. Or what's even more powerful without a calculator is you could take a look at this and say, all right, how can I rewrite 32? Well, I can rewrite 32 as, or if I can rewrite it as a power, I can rewrite it as 2 to the 5th. And that's so powerful because 2 to the 5th raised to another, that means raised to another power, I can write that as x to the 2 to the 5th times 2 over 5. Put that over 1, those are going to cancel out. I'm left with x equals, 2 to the 2nd power, which equals 4. And there you go. That's your answer.